Hello, what's up class? Today in this video tutorial I'll try to explain some basic signal processing concepts. Let's start from the circle. The circle has a sort of relation with the signal, with electromagnetic waves, and how that's I'm going to explain here. Let's take a pen. Okay, so this is a circle and we have a radius, and this is the point, and if you move around the boundary of the circle all along from first point and then reaching at the starting point, this is called one cycle. This is called one cycle. So if we have one more cycle over it with some angle, we'll have like this. If we increase circles, we'll end up with this. So at the moment, we are looking at this circle from upside, and if we have a lot of circles place one over the others. In real world, the examples, if I quote here, would be the bangle. Have you seen any bangles? Bangles, the circular bangles that looks like a spring. When you extract that bangles, when you extract that spring, bangles look like spring. When you stretch that and you look at from this side, if you look the bangles from this side, you will see like this, and from here, from this point and this point up to this is one cycle. If you have a wave like this and you flip that here, you will have a cycle. You will see a circle from a specific angle. So the wave has relation with the circle. You know, this is the amplitude, and this amplitude is actually the radius of the circle. This amplitude is actually the radius of the circle. And let me clear that now. Okay, so the amplitude is actually the energy or strength of the waves. So if you see, I'll explain later. So from one trough to another, this distance is called lambda. And this is one cycle. You see there is another cycle. So if we start from here, you will have one cycle, and then second, and then third. So in this signal we have three cycles. We have three cycles. Okay, if these three cycles if you see this, if you travel along this and make one circle and then another one and then another one, so this will take some time. So the number of circles completed in 1 second is called frequency. So in this case, let's suppose the time here is 1 second, and if in 1 second we have 3 cycles, this will be known frequency of this signal. Okay. And another important thing regarding this signal is that it is a sine wave. Sine or cosine wave, these are periodic signals. Periodic signal is the one in which a certain point repeats itself, and after a certain period the point will appear at the same location in the timeline. I'm going to erase this. So here we can see the circle, and this is the radius, and the radius is amplitude, and this is one circle and another one and then third one, and that is all completed. If these 3 circles are completed in 1 cycle, we will call it frequency. I already explained those. And you can see the radius and the angle here. So if this vibration happens in 1 second, we would say that this sine wave had a frequency of 3 cycles per second, or 3 Hz. Information can be transmitted on wires or wireless by varying some physical properties such as voltage or current. So varying properties are maybe voltage or current. So if we have 5 volt and minus 5 volt, and the voltage is varying in between these two ends, and with the passage of time we will have some sort of signals like this. So there are not only one physical parameter, voltage, we have current, and we have many more. We will discuss it later. So by representing the value of this voltage or current as a single value function of time f of t, we can model the behavior of the signal and analyze it mathematically. So once we represent the physical property of something that is varying with some time, we can analyze the behavior of the signal. Virtually everything in the world can be described via a waveform, a function of time, space, or some other variables. So for instance, sound waves or electromagnetic fields, the price of your favorite stock versus time. The Fourier transform gives us a unique and powerful way of viewing these waveforms. So keep in mind this thing, Fourier transform. Okay, I will explain this later. So what does it do? It gives us a unique and powerful way of viewing these waveforms. So we have waveform, and this is in time domain. So this waveform has some information inside, and the time domain and the Fourier transform can give us some insight of this waveform. The Fourier transform is the tool that breaks a waveform into an alternate representation characterized by sine and cosines. The Fourier transform shows that any waveform can be rewritten as the sum of the sine waves or cosine waves. So let me explain that. Let's suppose we have this signal. So all signals like this is actually made up by many simple sine waves. This is a sine wave. Okay? This is also a sine wave, and this is also a sine wave. So when you add them, you might get these things. So a signal or a waveform is actually sum of many frequencies. So we can say this is a sine wave with frequency f1, this is a sine wave with frequency f2, and this is a sine wave with frequency f3. So any waveform is actually made up of those sine waves. So this is in time domain. Okay, so this is in time domain, and this is time t1, and this is time t2. So signal in time domain will give you the signal value at any instant. For example, you can find what would be the value of this signal at time t1 and what would be the value of this point in the signal at time t3. But this signal will never give you an information about what frequencies are there inside, the constituent frequencies. So for this we transform that into another domain. This is time domain. In another domain that is called frequency domain. So this like f1, f2, f3, and this is f4. So for example, if you convert that into frequency domain, you will find out that you will see that how many frequencies are here and which one in this waveform. And how we gonna convert that waveform, the time domain function, into frequency domain function? This can be accomplished by Fourier transform. There are many tools, but one of them is Fourier transform. So Fourier transform transforms the waveform in time domain into frequency domain. So if this is f of t, a function of f of t, we will have a frequency domain with phi f. There is an example. We have this original waveform. So I'm going to remove that. Okay, and you can see this waveform is not a sine wave, and this is apparently, this doesn't look like a periodic function. It is a periodic function. So we have a simple fundamental, first fundamental frequency. If you look at this frequency, if you look at this wave or signal, we can see that the amplitude, this is 0, the amplitude is 3. So this has amplitude of 3, and this is the time in seconds, and if we approximate it, so it says that it is 6.2 seconds. So at 6.2 seconds we have this, and this is the complete cycle. We started from this point and then we go along the wave, we cross the zero level and we reach at minimum value, and when we are getting higher values we cross the zero level and we came back to the level from where we started it. So this is the complete cycle. So this is one cycle completed in 6.2 seconds. So I took that signal here. Can you see? Do you believe that the original signal and this are the same? What is your answer? They are not same. Obviously they are not same. So we are going to increase, we are going to try with another signal. So this time we have a signal with different amplitude, like 6. The amplitude is 6 and the time is same, 6.2. In same 6.2 it has 2 cycles. The frequency is 2. So you can say that this is actually this waveform has double frequency as compared to our first one. So if you add them both, if you add them, you will get this one. You see? So now you will see that this waveform get a little bit similar shape with the original waveform. So what I'm going to do, I'll go to get another sine wave. We have first sine wave with frequency 1, second sine wave with frequency 2, and third sine wave with frequency 1, 2 and 3. So this has 3 times, this has a 3 times frequency, this has more frequency, 3 times more frequency than the original one. So you have a wave with 1 Hertz frequency, no, not 1 Hertz, but in the given time it has 1 frequency, and this has double the first one, and it is triple the first one. So if you add those 3, you will get this one. And now you see it is more closer to the original waveform. Now I'm going to add fourth one. So once you have this and this waveform and this waveform and this waveform, and when you add those 4, you will end up with the original waveform. So from this example we can see this signal is made up of 4 sine waves with different frequencies. If I name that like G, if I name that G, so the G is equal to, and this is, let's suppose F1, this is F2, and this is F3, and we have F4. So F1 plus F2 plus F3 and plus F4. So we have 4 sine waves, and we got this one. Alright, so we move from here to here, but we can also move from the original signal to the constituent frequencies. So if we apply f of t on this Fourier transform, if you apply Fourier transform of this, you will get those 3 sine waves signals. So you can go through with this. This is not that much difficult. Okay, so this is a Fourier series equation. Fourier series equation. So from equation, don't be scared and don't go into detail. But from there, you can see this is a signal, and this signal is made up of 1, 2, and 3 components. So what is this? This is a constant. This will be some constant. If I speak in signal processing language, this is a constant value. Let's suppose 5. So if this is 5 and this is -5 and this is 0, so with the passage of time, the wave of this constant would be this, a straight line. And here we have summation m is equal to infinity am cos 2 pi mt of t. This is time period. Okay, this is time period, and the time period, 1 over time period, is actually equal to frequency. So recall your schooling trigonometric in mind. So this says that we have summation of this cos function, sum of cos function, where from where to where, 1 to infinity, and the sine wave is also is summing here 1 to infinity. So the signal is actually the sum of infinite sine and cosine waves. Let's move on. Here A0, AM and BN are the coefficients for the Fourier series. So if we want to approximate a periodic function f of t with fundamental period t with Fourier series this, so what would be the optimal Fourier coefficients for AM and BN? So let's start from the first term, this. So the optimal one for A0 value is this one, 1 over t, 0 to t f of t into dt. The proof of this you can find it on Google. In mathematics, but I'm going to explain that what is the interpretation of this equation. In mathematics, this equation is actually is an average. So this is an average value. So let's see the example. We have a square wave here. We have square wave, and the value is oscillating between 0 and 1. So what would be the average value between this is this one. So if this is the g of t, if this is the g of t, if this is the g of t, if this function is g of t, this one, what would be the value of A0? This would be 0.5. This would be 0.5. This is these are the constant values, constant coefficient of Fourier series. Now similarly we have AM and BN. Here I have just made some mistake, and this should start from m is equal to 1. We have seen that an is 0. So if an is 0, whatever is there, it's multiplying, so the whole term will be 0. That will go there. So 1, 2, 3, there are 3 terms. If you increase it to 7 terms here and 7 terms in sine, you will have a very similar look like a square wave. And if you add more terms, it will gradually go identical to the square.